So for this video, we're going to expand our notion of integrals to consider functions of two variables. So let's go ahead and motivate this with an example here. So let's suppose we have a pile of snow, and at any point xy, the height of the snow is given by the function h of xy. So here's our pile of snow that's in green for some reason, but all right, so this is a fairly familiar surface for us, but we're just going to call it h of xy rather than giving it a particular name here. And maybe we want to calculate how much snow is actually in this pile. So recall in Calculus 1, when we wanted to approximate the area under a curve, we used rectangles to do that because rectangles were something we knew how to calculate the area of. So for instance, here we have a left-hand sum approximating the area under a parabola here. And notice we basically took this interval from -2 to 2, and we broke it up into smaller intervals and used rectangles on those smaller intervals, and the height of the rectangles was the height of the function at the left edge point of each subinterval. So we want to do the same type of idea only in 3 dimensions. So to approximate the volume under a surface, instead of using rectangles, we'll use boxes, which we can think of as just the obvious 3-dimensional analog of a rectangle. So let's suppose we want to calculate the amount of snow in that pile, and we want to consider our x values to be between -2 and 2, and our y values to be between -2 and 2. So let's look at the level curves for our function. So here are some level curves for us. And so what we can do is we can take that region here, this rectangle, in this case it's a square, but in general we have a rectangle, and we can break it up into smaller rectangles, or in this case smaller squares, just like we broke our interval up into smaller intervals in the Calc 1 case. So here you see we divide this square up into 4 smaller squares. I'm going to just start referring to them as rectangles, even though they're squares. A square is just a special case of a rectangle, and this gives us a little bit better language because in general they'll be rectangles and not squares. So we break these up, and then when we were doing Riemann sums in Calc 1, remember we picked like the left edge point, the right edge point, the midpoint, or just any point in the subinterval to look at the height of the rectangle. So we can do the same thing here. We just, in each subrectangle, we just pick a point. So here we have our points that we picked in red. And so we can maybe say this is the first rectangle, second, third, and fourth. Just kind of going by quadrants here for this part. And so you can see we have those 4 red points. So what we'll do is we'll just evaluate the function at those 4 points, and that will be the height of our rectangle, our box. So then the volume of the box will be the area of this base. So for instance, if I do a box here, the area is of the base here is it's 2 width and 2 height, so it has an area of 4 here, and then it looks like its height is about 0.4 based on the level curve. So we would have a box of base area 4 and height 0.4. So if we denote those points as such, like I said, we form those boxes, and this should be 1, 2, 3, 4, not 1, 2, 3, 2. Typo there. And so here, this is a picture of what the boxes might look like. I didn't use those particular points on there to graph these. I just picked any points for choosing this just to give you an idea of what the boxes might look like. And so the volume of the snow is approximately the sum of the volume of the boxes. So that would be h of x1, y1 times delta x, delta y. So that's our first box, and then our second, third, and fourth box. So just to fill in, if we use those contours, like I said, we had the base areas are 2 by 2, and then we have these different heights. So we fill this in and get our approximation for the volume is about 16.4. Now, in Calc 1, we would start with a few rectangles, but as we wanted to get a better and better approximation, we used more rectangles, so we divided the interval into smaller pieces, getting more rectangles, which gave us a better approximation. So we take the same approach here. Now see, we've taken our square, our rectangle here, instead of using 4 pieces, we've broken it up into 16 sub-rectangles now. So now this will give us more boxes. So we pick a bunch of points. So here's sample points we could pick for this. One red point in each rectangle. And then we form the boxes with the heights of whatever those level curves are. So it might look something like this. And you can see this is looking a little more like what our snow pile looked like. It's still not particularly close, but it's looking a little closer than what our original one did. And again, we can form the same idea. We have the volumes is approximately the sum of the volumes of the boxes. In this case, we have delta x and delta y are equal to 1 because we've broken them up into smaller pieces. So you can see each rectangle here has width and height 1. And I didn't fill in the values for all the h, x, I, y. It seemed to be a little tedious to do, and I think that's clear what's going on for this. Now, we can also add a bunch more boxes if we want, and we can see how with the more boxes we get, the better the approximation is getting to what our snow pile looks like. So I think these are like 40 in each direction. So the x and y intervals are each broke up into 40 pieces. So you can see this is starting to look a lot like the snow pile. So now let's consider a little bit more general case and how this sets up for general. So let's just take any z is equal to f of xy and consider some region. In this case, we don't have to have a square here. We're just taking x between a and b and y between c and d. And there doesn't have to be any relation between a, b, c, and d here. So we'll take our delta x. We're going to break the interval from a to b up into m pieces. So take delta x to be b minus a over m. And break the y interval c to d up into n pieces. So delta y is d minus c over n. So that just equally splits up the interval. And then we just define our values x0 through xm by xi is a plus I delta x. So each time you move over, you're moving over by one more delta x. So x0 is just a, x1 is a plus delta x, and so on. And then do the same thing for the y's. And now for each of the rectangles, so this is how we're denoting a rectangle, this interval across this interval gives us one of those rectangles. For each one of those, we just pick some point in that rectangle, call it Pij, and then we can form the Riemann sum here, where we're just summing over all of the volumes of all of these possible boxes that we've chosen. So this is the same thing we just did for the snow pile, just a little bit more general. And so now we can finally define what our definite integral of a function of two variables is over a region. So our notation here is we use two integral signs to show that it's an area integral. So we're integrating in the xy plane instead of just an interval. We put the r subscript there for the region we're integrating over. And then we just take the limit as m and n go to infinity of our Riemann sum. So same idea as we did for one variable functions. We just want to have more and more and more boxes so it gets a better and better approximation. One other thing to note here is we might want regions R that aren't rectangles. There's no reason everything we want to look at is going to fit nicely into a rectangle. So what we can do for that, we're going to see how to do general regions in class and how to actually evaluate some of these integrals. So far, we've just defined them as a limit of Riemann sums, and you probably remember from Calc 1 that those aren't so fun to calculate. So we're going to see how to do these using the fundamental theorem of calculus and make them iterated integrals. So we do two integrals, one in x or y, and then the other in whatever variable the first one wasn't. But we might want general regions. So what we can do is we can just take whatever general region we have and put a big rectangle around that whole region. Then we can divide that big rectangle up into a bunch of subrectangles, just like we did above. And then when we form the Riemann sum, we're only going to take those subrectangles that actually sit inside our region R. So if our region's a circle, we're going to not have rectangles exactly covering every part of the inside of the circle. But as we get more and more rectangles, they'll completely fill out the region, even if it's not a rectangle. So you're always going to be missing a little bit, but in the limit, you'll get all of it. So that sets up what we're looking at in terms of integrals of two variables. We'll actually, like I said, we'll see how to actually evaluate these in class when we look at iterated integrals and actually do some calculations.